So today is the only day when in the afternoon session we are doing lectures, because the lectures we are doing are still very brute fashioned. So we ended before lunch talking about difficulty in processing the huge amount of data which we are producing. And I'm not even coming to data being produced by machines. We're only looking at the data which a human being is generating or list of humans are generating. So the other problem हमारे साथ ये होने वाली है कि how do we make right the history of our world compared to our past generation. 2000 साल पहले लोग एक पत्थर का 4 लाइन लिख के रख देते थे and that was the history. उसके बाद एक किताब लिखी जाती थी. अभी the amount of data which we're producing is very big. So historians of future will have got a very tough task looking at what we do. The issue which we also have with artificial intelligence is the amount of data which we are giving to a central machine. And the fun fact is at one hand, we are not happy to give data to our own near and dear. Right? अपना personal data हम लोग काफ़ी secure करके रखना चाहते हैं. बट एक कंप्यूटर को देने में हमें कोई दुख नहीं लगता. Despite the fact that computing machine is way more powerful to extract information about us than individuals are, right? अगर हम किसी को अपना medical history बताएं तो शायद आधा तो उनकी समझ में ही नहीं आएगा. The machine will figure it out, and I still am happy to give to machine. And this is where things become very different. So sitting in India, आपको लगता होगा कि the entire Western world thinks in the same way when it comes to security and privacy. There's a very subtle difference in the way Americans look at it versus the Europeans look at security and privacy, particularly when it comes to data. And then, of course, there's a very different way in East we look at data, for that matter, China, or for that matter, even India. So Americans generally do not, in general psyche of American population is not to trust the government. So they're unhappy with the government keeping a lot of data, but they're happy to give it to Google or Microsoft. So companies can't do anything wrong. In Europe, we are highly unhappy to give data to companies. This is why you have got things called GDPR, General Data Protection Regulations. But we are okay to give data to our government. Right? This is despite the fact governments in Europe have not been very nice when it comes to personal data. If you know the history of Europe, it has been very problematic. I guess in China, people don't have a choice. Government wants to take all the data and it has all the data. It depends upon how long I want to live in India. ठीक है क्या करेंगे. So in India we have got a situation wherein the government says if you want to give your data to us, we will keep it, but we are not forcing you to give the data. By the way, if you don't give the data, आपकी life very miserable होगी. Right? A very good example is the biometric Aadhaar card. Can you do anything in this country without Aadhaar card now? Legally you can, you should be able to. I don't have an Aadhaar card, I can't have an Aadhaar card, I'm not a resident Indian. But every time I go to a bank, I get the same thing, Aadhaar card attach कर दीजिए. कहाँ से Aadhaar card attach कर दे? And there lies an issue when we have a centralized system. For most practical purpose, Aadhaar system is very safe and secure. But there are subtle things. For example, there is no way to delete a person's Aadhaar card if the person has passed away. Right? So my father has passed away, but if somebody wants to use that Aadhaar card, the same mobile phone number, the person could continue authenticating against his Aadhaar card for times immemorial. Right? So we have subtle issues which we have not thought about, but at least India is a democracy, government cannot force you to give the data. The problem stays that our life is very distributed. We are recording different snippets of our life in different junctions at different points of time. How do we secure it? And also what happens when we die to our data are open questions for our society to answer. Right? क्योंकि अभी तक हम लोग डेटा कलेक्शन फेज में थे, जितना डेटा कलेक्ट हो सके करो, अभी वही कर रहे हैं, राइट? डेटा सेंटर्स में डेटा लिखे जा रहे हैं, फोन, जितनी ज़्यादा मेमोरीज हमारे पास आ रही है उतना ज़्यादा डेटा हम प्रोड्यूस कर रहे हैं, राइट? So a very good example, I started working as a camera developer. मैं cameras बनाता हूँ, right, as a hardware person. So our parents' generation had 35 photographs of their wedding, and the number was almost always 35 or 36. पता है क्यों? पुरानी रील में 35 फोटो, तो एक रील वेस्ट किया उन्होंने. बट मोर इम्पोर्टेंट, दे न्यू एवरी फोटो के बारे में. इस फोटो में ये खड़े थे, इस फोटो में ये हुआ, इस फोटो में वो हुआ. आवर जनरेशन प्रोड्यूसेस 2000 फोटोज ऑफ देयर वेडिंग एंड हैव एब्सोल्युटली जीरो आइडिया अबाउट ये फोटो कहाँ से हुआ था. So despite all the AI we are using to tag these photographs and produce information, we are still not keeping that amount of information. And there brings the second issue, which is this one, the selective use of data. So you assume that once we produce a huge amount of data, people will be able to use the data as a whole. Now we talked earlier that we have selective use of data ourselves. We human beings like to only pick up data which we like to hear about, right? If we follow the Indian cricket team, we are not reading the news right now क्योंकि वो मैच हार रहे हैं. जब जीतने लगेंगे तो फिर से न्यूज़ पढ़ेंगे. Right? It's a natural thing which we do. The problem happens when institutions also start using selective use of data. They should ideally be using data as a proper format, but अगर वो भी selectively use करना शुरू करें, then we're not actually using data properly. The other things is the factory jobs are being lost. Right? The classic factory में जहाँ हम लोग काम करते थे with a large number of people, that large number of people has become less because of automation. और single site factories develop की हैं तो हम workers का कुछ right बढ़ा था, but that right has also started going low now. Now we are having distributed factory. पहले आप कंप्यूटर बनाने के लिए there was a factory in US or Germany and that did the whole task. या कार बनाने के लिए वहीं था. अब तो सॉफ्टवेयर बनाने के लिए हम 10 डिफरेंट जगह सॉफ्टवेयर सेंटर्स रख सकते हैं and I can distribute workload from here to there in a very easy fashion. पहले पूरे बनाने के लिए I had to establish a new factory, retrain everyone there, and only then the data work process will move there. Right? Now, India benefited from this. Because a lot of jobs moved from Western world to India, right? Call center हो, offsourcing हो, या फिर software development का काम हो. काम तो हम दूसरे जगह कर रहे थे, हम इंडिया में बैठ के कर रहे थे, हमारी सैलरीज लो थी तो हम compete कर पा रहे थे. The question to be asked is, कल को अगर next series of countries अगर technically अच्छी बन जाती हैं, say for that matter Africa, तो हमारे jobs वहाँ जाएंगे. Indians are already very costly people to hire. हमारी सैलरीज काफ़ी अच्छी हो गई है, राइट? एक तरफ से हम लोग खुश हैं, एज ए इंजीनियर वी आर बीइंग पेड वेल, बट दैट मीन्स कंपनीज हैव टू पे मोर टू हायर अस, एंड दैट्स नॉट नाइस. आई मीन आवर यूनिक सेलिंग पॉइंट इनिशियली वाज कि हम सस्ते वाले मजदूर हैं, और हम ज़्यादा पैसा मांगेंगे तो फिर दिक्कत होगी. बट एट द अदर एंड वी शुड बी आस्किंग मोर, वी शुड बी गेटिंग इक्वेटेड. But once we are being equated in talent and innovation, then our economic factor is gone. Okay? So hopefully by that time we will be innovative enough to be equal to innovative factor. So this is what happened. The whole distribution of factory has been good for some economies. It has been good for economies like India. It has been bad for some economies which have lost their personal strength. It has been good for, say, places like Bangalore and Hyderabad. They were able to have large number of engineers. But it has been bad for traditional technological giants. At one point, Rourkela, Bhilai, Jamshedpur and Bokaro were the technical giants of India. Now they have lost their shine. Okay? Now this raises new questions. अभी तक हम लोग कैपिटलिज्म की बात कर रहे थे, wherein we will have free market, free labor. But now people are already talking about protectionism and nationalism. right? US is already talking about restricting, हम बाहर के लोगों को नहीं अप्लाई, ये हमारी टेक्नोलॉजी है, एक पर्टिकुलर GPU और CPU design is ours and nobody else can use it. And the moment you start doing that, कि ये हमारा है आपको नहीं देंगे, तब जंग के आसार बनते हैं, right? पहले युद्ध किस चीज पर लड़ा जाता था? पानी पर, गेहूं पर, अब द नेक्स्ट आस्पेक्ट जर्ज और जमीन के बाद एक शायद टेक्नोलॉजी भी हो जाएगी जिस पर हम युद्ध लड़ेंगे. The other thing which could happen is people start technology itself. ये क्यों रखें हम? AI ने तो हमारी नौकरियां खा ली, हम नहीं यूज करेंगे. And this is it happened in one way. जैसे US और UK में बहुत सारी कंपनियां जिनका लोकल कॉल सेंटर था वो प्रमोट करती हैं, कॉल सेंटर बेस्ड इन UK, not based on India. And would that start affecting us? Would there be a bank which will say कि we do not process your data at all, come and do banking with us? The last question which we don't know the answer is, what will happen to cities? Why did cities get established? Because we needed a large number of people to work at one place. अगर हम distribute कर रहे हैं, तो why do we need a major metropolis? So the question then is, will we go back? We moved from villages to cities. Remember, हम छोटे-छोटे गांवों में रहते थे. We moved to cities because workplace consolidation हुआ. अगर distribution हो रहा है workplace का, will we move back to villages? And that's an open question for us. It's an open question for coming generations. What will happen? The last thing, machines are not going to take over. I mean, artificial intelligence is all still seems like an NP hard problem. So अभी immediate, at least आप लोग की नौकरियां लगेंगी ही, आपकी generation के आगे का कहना ये है. But the thing which is actually changing is this. So मेरे previous generation, my generation's professors learned bipolar junction transistor in their schooling days, university days. And they had to learn about MOSFET transistors while teaching us. So एक change of technology हुई. मेरे generation के लोग, they were learning computer vision, simple computer vision problems. Then machine learning हुआ, then neural network, then deep learning हुआ. The sheer change of pace of technology is so much that the old model कि हमने आपको 4 साल पढ़ाया, 6 साल पढ़ाया, आप जाके नौकरी कीजिए for the rest of your life, is dead. So does that mean now you'll be trained for 4 years, go and work for 10 years, and you have to come back to university to be retained at early stage of your life and then work for the rest stage of your life? Has to be revisited. Right now you're looking at all these neural network models. I mean, they may be dead tomorrow and some other thing could come up. And the pace is fast. So we will have a much bigger role. Maybe we might come back to a model wherein the fixed time of education will have to be reduced in favor of education at a later part of your life. The idea of 25 में नौकरी किया और 60 में retire किया has to be revisited again. Good. Now this is just some interesting fun bit for you. Do you guys know this, right? The evolution of telephones. How many of you can use this phone? Okay. So my parents' generation was this phone people, right? And they found it very difficult to press something because you don't get that feeling that grrr, बजना चाहिए कि हाँ हमने 4 dial किया. How do you know you have done something wrong? Right? Now you guys are so we were the button pressing, we are the thumb pressing generation, right? Thumb pressing के बाद index finger pressing generation शुरू हुआ. And that has hurt me quite badly. My finger strength have gone down. I just had a hand surgery the other day because my fingers are very much, and even on a Mac, they're constantly going this way, right? The question is, how do you train people like me who are getting a bit older? We are crossed on the stage of 40 and new technology, okay, right now I can pick up. But I will also reach a stage wherein, despite being an engineering professor, we will not be able to cope up with the technology. And you will reach that stage as well. And while it might sound very silly, हम लोग अक्सर, I'm sure जब आप अपने पेरेंट्स या अपने elderly family members को फ़ोन यूज़ करना सिखाते हो तो इरिटेट होते होगे. सिंपल सी बात तो है, सेटिंग में जाके डायल टोन बदलना है. Right? How difficult it is. So it's a very nice, let's see if the video works and if you can see the sound or not, we'll see how it works. But it's a very nice video which I often showcase to show any technology is hard for a learner to use. Can you hear the video sound?
Ansgar? Ja, det er jeg, ja. Ja, så bra, ok. Ja, hei du. Hei du. Ja. Ja, hva gjelder det? Ja, det er denne her. Ja, du sitter. Takk. Ja. Jaha. Ja, så jeg har ikke fått gjort noen ting hele formiddag, ja. Nei, jeg bare tar tid, så skjønner vi holder på å legge om til et helt nytt system, og da skal alle ha hjelp på en gang. Ja, ja. Så du kommer ikke inn i den, eller? Nei, den bare ligger der.
So it's a video made of a medieval tech support person who is asked to come and help the technology. The new technology has been introduced, so of course it doesn't work.
Okay. Har du forsøkt å åpne den? Ja, åpne den? Altså, hvis det hadde vært så enkelt, så hadde jeg jo ikke tilkalt helpdesk, hadde jeg vel? Nei, det er sant. Nei. Vil du ha en kopp varmt vann? Nei, det skal være fort gjort. Det skal vi se. Du bare gjør der. Sånn. Ja. Da er du i gang. Ja, altså så langt kom jeg også. Ok. Men så stoppet det opp, og så var jeg redd for at noe av teksten skulle forsvinne, så jeg turte ikke å gå videre. Ja, ok. Nei, men du skjønner at inni her, så ligger det kanskje flere 100 sider med lagret tekst. Så for å komme videre, så tar du tak i et ark på den måten her, og så liksom blar du over på neste side sånn. Da fortsetter teksten der. Jeg blar, altså? Du blar, ja. Men når jeg skal tilbake da? Ja, da bare blar du tilbake igjen. Tar tak der, og så er det sånn. Der, så er du tilbake til den teksten du hadde, sa. Ikke noe ok, så den slutter der, og så fortsetter den der, ja. Ok, men når jeg skal avslutte for dagen, hva gjør jeg da? Da bare slår du sammen permene på den måten der. Sånn. Da ligger alt lagret inni der. Altså, jeg risikerer ikke å miste noe av teksten her nå, altså. Nei, alt ligger lagret inni her nå. Da må du i tilfelle sette fyr på hele greia. Det er kanskje lite sannsynlig. Ja, ok. Nei, men for det er noe med det at liksom, når du har holdt på med skriftruller, så tar det litt grann tid å konvertere til å bla i en bøk. Ja. Ja, men du, en til før du går. Jeg må bare gå gjennom en gang til. Altså, jeg åpner sånn, og så, hva har du kalt det? Blar. Jeg blar. Ja, blar videre. Blar frem og tilbake. Ja, teksten ligger der hele tiden. Ja. Og når jeg er ferdig, så bare lukker jeg den. Flott. Fint det. Kjempefint. Ja, men du, vent, ikke sant? Nå er den sånn igjen, nå får jeg ikke åpnet den. Nå får jeg ikke åpnet den. Nei, du har den på feil side. Du må åpne fra andre siden. Så det er ikke likegyldig det, altså? Du må åpne fra den siden der. Sånn. Der. Der nå. Ja vel. Har du lest manualen, eller? Manualen? Jeg skal følge med som manualen som brukerveiledning. Det er sikkert den der. Der, vet du. Åja, den ja. Står alt sammen. Ja, men ikke sant, der har du samme problemet. Får den ikke opp. Ok, det skulle vi kanskje tenke på.
So bottom line is, any technology is hard if you're moving from one format to another. Right, let's go back to computers. Enough of history. Okay? इसके ज़्यादा हिस्ट्री हम लोग कंप्यूटर साइंटिस्ट नहीं झेल सकते. Good. So we'll now look at the early architectures and see how we have gone back to the current form of computing which we do. This is also important because you need to appreciate why AI models are running GPU clusters. But more importantly, why they consume so much power and energy. So 3 things are interesting here. One is the Konrad Zeuss's patent of 1936. This is the German computing industry. Von Neumann's seminal paper, which introduced the von Neumann computing machine. And then, of course, the Alan Turing's automated computing engine. So have you guys been taught about von Neumann architecture in your school? Some of you guys would know that. So most of the computing machines which we have from hardware point of view, they're von Neumann machines. So originally, the idea is this: how do we design a computer? Where do we do the input? Where do we do the output? Where do we do the control? Where does the memory lie? And there were 2 original architectures of memory. One was the Harvard architecture. which did this. So this is a typical model which you might have seen. There's input, output, there's control unit, arithmetic and logical unit. It behaved in having a separate instruction memory and a separate data memory. The idea was what you're going to do will be stored separately than the numbers which you're going to play with. The Princeton architecture, or the more commonly known as von Neumann architecture, this is on which we have most of the machines. We have a single memory which stores data as well as instruction. And then we have input, output, and in between we have CPUs. Right? Now with time we have made our CPU go fairly fast. What's the clock speed of your processor? 3.2 gigahertz. That's where most of this has plateaued, right? Earlier it used to increase every generation. What's the clock speed of your memory? ये वाला कंप्यूटर बेचने वाला नहीं बताया था, right? Even when you buy a mobile phone, they will talk about 16 GB RAM है, 64 GB RAM है. कोई उसका स्पीड नहीं बताता. प्रोसेसर का स्पीड हमेशा बताते हैं, right? So memories are inherently slower than processor, right? And this is why we have, and then there's a second aspect, which is the communication link. This does not scale the same way as a processor and memory scale. So the transmission link is significantly slower than processor and memory. So as a result, we end up having what we call as processor memory bottleneck. Okay? Now, how does it affect us? In the computing design, we try to circumvent it by having cache memory on the processor. So आप लोग level 1, level 2 cache के बारे में पढ़े होंगे. There's cache you put on the chip to reduce the number of fetch. In modern day AI hardware implementation, the one which is taking the most amount of memory is not computing, not multiplying, not adding, but accessing memory from the. So memory में data stored है, उसको वहाँ से उठा के processor में लाना और वापस ले जाने में सबसे ज़्यादा हमारी energy खर्च हो रही है. I was going to not talk about human history, but computing history तो दो चार बोलना ही पड़ेगा. This is also because in most of the history courses in India, you primarily read at ENIAC and the British computing history. German computing history उतनी नहीं की जाती है. The German professor, I thought it was worth telling you about. So Konrad Zuse started in the Technical Hochschule in Berlin, which then became Technical University of Berlin. And he wanted to do engineering and architecture, and he found both of them to be very boring, as many of first-year students find. And then he ended up being a civil engineer. He joined an aircraft factory where he had to do a lot of hand calculation. So being a good engineer, he decided to go and make something to do with machines. So he ended up making this Z1 machine, and he did series of Z1, Z2, Z3, Z4 machines were made. So it's a very interesting thing because Z1 had read instructions from a 35 millimeter film. Unfortunately, Z1 was destroyed in bombing in Berlin, but we have got its performance speed. It worked at a frequency of 1 Hz. So we just talked about 3.2 gigahertz, right? It had a computing speed of 3 seconds. Of course, the weight was 1,000 kilos. And it costed 800,000 Deutsche Marks. On a rough estimate, you can say 1 Deutsche Mark was roughly 50 euro cent. So 400,000 euros for one computer. I will not talk about Z2, Z3. Z4 is interesting because this was a large enough machine. It worked at 40 Hertz clock speed. It took 4,000 kilowatts of power and it could compute in 0.4 seconds. So after making Z4, he decided to do his PhD. So all those who wanting to do PhD, kam se kam itna kaam karke shuru karna. He submitted the PhD thesis and it was rejected because he forgot to pay the fee in time. So all those of you who are complaining that bureaucracy bahut zyada hai, it has hurt other people as well. Now, one of the later days machine which he did was a Z5 machine, which could do addition in 0.1 second and multiplication in 0.4 second. Okay. It still costed us large sum of money. Now, the last one wherein he could do a clock speed of 140 kilohertz. So now you are going from few seconds to few milliseconds. So you could do multi-addition 0.3 millisecond. Do you know how long it takes for your computer or your mobile phone to add two numbers? Because these two are very interesting things for us. Addition of two numbers and multiplication. Because almost entire neural network is about multiply and accumulate. Multiply and add numbers. So from a power point of view, these numbers are really interesting. Anyway, so you can see these machines are huge machines. I mean, there's 1,000 kilogram machines, right? So we went from machines which are as big as that to machines which are as big as this, right? Which is more powerful than that machine and can store more amount. But these machines do not learn. The machine can only do what we ask it to. We program it to do it. Now, there are modern neural network-based machines or deep learning-based machines, AI machines. And a very good example which I give is the Google Brain project, which wanted to identify cat in YouTube videos. And to do so, it required 16,000 processors and 100 kilowatts of power. My 3-year-old daughter, if you give her a piece of bread, she goes around looking at cats and say, katta, katta, katta. So human beings, such poorly trained human beings can identify cats. Whereas when it comes to computer vision tasks, it is still a challenge. It's not a challenging task. There are very good algorithms to do it, but the amount of energy it takes is huge. So one of the source of this problem is the processor memory bottleneck, and other is our algorithms are actually very poorly defined. So back to von Neumann architecture, and so as we said here, that you have a large number of processors. So now you have 16,000 processors which need to talk between themselves. We need to extract memory from the bank, and we already said that the von Neumann architecture suffers from this processor memory bottleneck. So this is going to cause even more concern as we go further. The last year, the largest Google model consumed more energy in in inference than a transatlantic flight. So you could fly from here to London on a chartered plane, consume less energy than training one of these neural network systems. Now you can see why, even though I have asked you guys to be ready with your laptops, we can't do complex computation on your laptop. We would need a GPU cluster. And because we don't have a GPU cluster access here, we will not be able to write very complex programs. We'll only be doing with simple data. Okay? And here's a very good example of what is happening in performance memory bottleneck. Fine, this figure is a bit older. You can see processors have increased their clock speed significantly, and the performance has improved. Memory has also improved, but not to the same level. So this bottleneck keeps on increasing further and further. And then, of course, you have all the system buses which are used to communicate between processor and memory, which are also slow. You might ask, why is this interesting from neural network point of view? So let's go and see why is it interesting from neural network point of view. Okay. In the next half an hour or so, I will go through perceptron. So second year student, how many of you guys have come across perceptron? Doesn't ring a bell? Okay. Might sound like one of the... What was that movie series where you have got cars which could become a fighting... Transformers. Well done, you see. I have a 10-year-old son, so I have to watch these movies as well with my eyes open and brain dead. Good. So the motivation for our almost entire neuromorphic or neural network systems have been the brain, right? We think we are trying to make the brain. Remember one thing, the models which we use these days in deep learning algorithms have got nothing to do with the brain. They were inspired by the brain, but these are not the models which the brain uses. For two reasons, we don't know what the brain uses. And B, whatever basic we knew is what we used in spiking neural networks, but not in deep learning neural networks. Okay? So essentially, our nervous system does this. Something happens. We have got things which try to record something has happened. Then there's a neural net which basically tells do this. So for example, I'm sitting here, I see a motion happening on my periphery. Right? I can see my periphery motion better than I can see. In periphery I can only see motion, I can't see details. So I was growing up in a forest. By I mean human beings. We were in a forest. Peripheral motion happened, there might be a snake or tiger. What does the brain does immediately? Ta-ta! Look. And this is, we often say there's something happening at the edge of our eyes. So look, if there's a lion, what do? Sorry? Fight or? I would love to see you fight a lion. Whom should we bet money if he fights a lion? On the lion or on him? Both options, fighting as well as flighting. On you. Okay, we will do that. Now, this is a classic part of the brain. If we start, so we kind of know now which part of the brain does what. We don't know how well it does, right? So for example, we know Brodmann area 17, which lies at the back of my head, does vision. So we see from the eyes here, transfer the information to the back of the head. And then we have the primary visual part and higher visual part, something which just looks at parts of the brain, memory and other things which does that. Now, most common in the fundamental unit of our nervous system are these neurons, which appear in different shape or size. So essentially they have a cell body, they have some dendrites to connect to the nearest neurons, and then they have a long axon, and then they have synaptic terminals at the end of it. Okay. We generally have roughly 10 to the power 11 neurons. So we have a large number of neurons. We also have a dense connection, right? They are generally connected. Every neuron is connected to another 10,000 neuron or so. But they are very slow. A neuron barely works at a speed of millisecond. Okay? What's the speed of our computers? So 3.2 gigahertz clock speed of your chip, right? So let's take 3 gigahertz. So the clocks, we're now talking about tens of nanosecond speed. So our transistors are way faster than our brain. How do we make up for that speed loss? How are we still able to compute? And fine, we can't compute numbers quickly, but we are very good in inferring. Right? We're very good in knowing when danger is coming to us. Well, most of the time. So what we balance out, so we don't have very high speed neuron, but we have loads of them, and loads of them are talking to one another. And these neurons act as both the memory unit as well as the processing unit. Remember, in our computers, we had memory and processor separately. So nature has not, well, it has kind of a long-term memory, but most stimulus response function, it has evolved as if to make things together. We have kind of a 100-step rule. If something does not finish in 100 steps, brain kind of forgets it. It's not useful. So we generally do not take anything more than 100 steps of computation. The other interesting thing which the brain does, which we still don't understand how it does, is the amount of information it sends from one neuron to another is very small, at maximum a few bits. When we transfer information from one core to another core or from one core to a memory, it's generally a large amount. Even of one byte of information is already 8 bit for us. Let's do a calculation. How many camera pixels do you have? You all have cameras with you, right? You all are engineers. फोन खुद खरीदा था या फिर माँ बाप से को ब्लैकमेल करके खरीदवाया था, या फिर अपने सिग्निफिकेंट अदर से को ब्लैकमेल करके खरीदा था? That's the only reason when you should not know the technical specification. जो भी दे दो अच्छा है, फ्री का मिल रहा है. How many? 50 megabytes. Megapixels. 50. कौन सी कंपनी थी भाई जो 50 प्रोड्यूस कर रही थी? 64 megapixel, and you have just a single phone camera imager or 2 or 3 behind you. I mean, these days I often joke that there will be a time when this wall will be filled with cameras, right? 3. So another homework task. जब घर जाए अपने पास जो इलेक्ट्रॉनिक्स है उसकी थोड़ी स्पेसिफिकेशन जान जाइए, because it's interesting. So 60 megapixel, right? हम 60 लेते हैं ताकि कैलकुलेशन आसान होगा, और आप लेते हैं वीडियो, तो कितने फ्रेम्स पर सेकेंड का वीडियो होता है? ठीक है, 30 फ्रेम्स पर सेकेंड लिया आपने, तो 60 मेगापिक्सल इंटू 30 पर सेकेंड कितना हुआ डेटा? 1.8 गीगाबाइट, राइट? एक सेकेंड में, राइट? अभी 1 मिनट का वीडियो भी नहीं बनाया हमने, 1 सेकेंड का वीडियो बनाया. वी हैव प्रोड्यूस 1.8 gigabyte. Of course, we'll be compressing this video later on. But that's the amount of information which my camera chip is generating and sending it back to the processor. 1 सेकेंड के सीन को देखने के लिए. हमारी आंखें, आपकी आंखें जो मुझे देख रही हैं, कुछ नहीं बदला सीन में. They're not even sending information to your brain. They have done this thing. या सीन है, कुछ ज्यादा चेंज नहीं. अब अगर छत गिर जाए, तड़ाक से आपको ब्रेन को होगा भागो, कहीं मेरे साइड भी गिरने वाला है. We also have this theory called cortical prediction. So you all go back to your room, right? In your boarding school, और अपने घर पर जाते हो आपको एक दिमाग में आपकी एक तस्वीर बनती है कि हम रूम में जाएंगे तो यहाँ पर कुर्सी होगी, यहाँ पर चेयर होगा, यहाँ पर मेरा बुक्स होंगे. As long as things are like that, your brain does not register anything. Eyes ने देखा कि हाँ ये वही फ्रेम है, भूलो सबको. It doesn't even record that image. अगर कुछ गड़बड़ हुई, कुर्सी उल्टी रखी हुई है या फिर किताब पे, then your immediately brain says something is not right. Even though fact it does not remember immediately everything कहाँ पर. So a part of theory says that whenever we are going to a familiar room, a brain initially he some lacks like a generative logic, एक generate करता है image, ये वाला मिलेगा तब कुछ नहीं करेंगे. So the neural networks produce a significantly small amount of data in our brain, not the neural networks which we are going to talk about, right? The other thing is that while some neural networks are present at birth, so neurons form neural networks, okay? Most of it is developed through learning with time. With time, so some we know from birth. For example, दूध पीना है. Well, most of the kids know, not always. Say for example, cows calf. They know कि 2-4 पाँव में कैसे खड़ा होना है. हम ही गधे होते हैं, हमें 6 साल लगता है खड़े होने पर, और 18 साल लगता है मैच्योर होने पर, और इफ यूर ए बॉय 40 साल लगते हैं मैच्योर होने पर. उसके बाद भी मम्मी बोलती है मैच्योर नहीं हुए हो. Right? So we learn by appreciation. Now this is where the other thing is this. Look at the amount of time we give for learning for ourselves. Just to identify something is red color, we give about 3 to 4 years to identify that. Okay? We're not giving that 3 to 4 years for a computing machine to learn. So speed और power का game खेल रहे हैं हम यहाँ पर. Right. So we are going to make artificial neural networks of some sort. So that was that human neural network. Now I've taken an old definition of artificial neural network from the book of Alexander and Morton as to what is a neural network. So the definition goes, it's a massively parallel distributed processor Remember, till now we were talking about one processor, one memory. Now we're talking about massively parallel distributed processor, which has a natural propensity for storing. So every processor is storing. Okay? It's not separate from this. What is it storing? Experimental knowledge, and is making it available for use. Okay? It resembles brain. It's not brain. It does not copy brain. It resembles brain in that it... So, morning parents call, now parents-in-law, and they are the more dangerous call. Or could be wife. So put your phone on aeroplane mode. Okay, so it resembles brain in that it acquires knowledge through some learning process. We don't know what the learning process is now, right? कोई learning process है जिससे ये सीखता है कैसे क्या करना. And the interneural connections, जो strengths है, जो neurons के बीच के जो strength है, दो जो उनको हम synaptic weights कहते हैं, they are storing this knowledge. Right? So the only similarity between the neural networks and artificial ones and the natural ones are that the way we store the weights. The definition of learning, आप ये सवाल पूछ सकते हैं, some learning process, what does it mean? So learning process, very mathematically defined, would be there is this task which you are doing in an environment E, and then there is a learning process L, and the environment dictates how you will do the task by telling you whether you did the task well or not. Okay? Or there is some measure of telling you that this is what the task should be done. Now, we'll go to the very, very fundamental approach. To make a neural network, we need a neuron, and this is the only theory which you have to remember. अभी तक आपने देखा होगा मैंने कोई equation नहीं फेंका है आपके ऊपर, right? As you can realize, my father was a mathematician, and he always told कि engineers को तो maths आती ही नहीं है. Despite the fact कि maths Olympiad में medal जीते थे, but for him we were never a mathematician. So देख रहे हो कि I rarely use equations while explaining. We'll use them later on, but one equation is coming. So warning. So essentially what are we doing? We have got n number of inputs. This is the simplest model of a neuron or a perceptron we do. Each n number of inputs, each input gets multiplied by a weight. We add all of these results and then apply some activation function on it. What activation function is, we will see in a second. Okay? And then that gives us the output. The activation function could be something very simple, which basically says if all of this summation is anything lower than 0, make my output 0. Or if it is more than 0, make my output just 1. So it could be a binary activation function, or it could be a smoothly changing activation function. Good activation functions are sigmoid or tan H, or it could be a rectilinear linear unit. So later part we will see what kind of activation functions. So our bottom line is this. Oh, still no equations. I forgot to write the equation. Good. So we multiply each input with its own weight, add them, apply this function on top of that, and that's our very simple neuron. We could create these neurons in hidden layers. We could create layers of these neurons, and if there are some sort of hidden layers, we call it deep learning. We could have multiple layers, and we could create in any way sort of communication. This is where a large number of neural networks which have evolved. We're not going into large number of neural networks today. We are only going to say is that in a simpler way, we could have two-way flow of information, aka so neurons data produce करते हैं अगले न्यूरॉन के लिए, और अगला न्यूरॉन एक एरर फंक्शन जनरेट करता है पीछे वाले के लिए कि भैया आपने सही काम किया या गलत काम किया, राइट? अगर आपने सही किया तो आप जो कर रहे हो करते रहो, जो आपने गलत किया अपने आप को चेंज करो. It's as simple as that. Now you might think कि हम क्यों सिंपल ले रहे हैं और अभी तक हम प्रोग्रामिंग शुरू नहीं करना है, राइट? देखा जाएगा प्रोग्रामिंग. Let's see if a simple neuron as simple as that, can it do actually anything meaningful? So I will take an example again from Haken's textbook, which is to say can we identify between a banana and an apple, or banana and an orange or an apple? Let's take a banana apple sensor. Okay, so we have got a factory line of things where fruits are coming. All we want to is to classify whatever we have recorded, is it a banana or an apple? As a human being, we are perfectly fine to identify this thing. Let's assume we have put 3 different sensors on there. One which looks at the shape of the object, and these are just binary sensors, right? All the sensor does is it gives an output of 1 if the object is round. It gives an output of -1 if the object is elliptical. We look at the texture. Is it smooth? Is it rough? And the weight. Is it more than 1 kilo or less than 1 kilo? If it's more than 1 kilo, we get an output of 1. Less than 1 kilo, we get an output of -1. So very simple sensor. Each sensor is a binary. It gives me a 0 or 1 kind of output, and I want to use this to identify apple and banana. At this point, you might ask, Professor, this is redundant because shape itself should be enough, right? Maybe you should put a color sensor, but we don't know that right now, do we? We haven't learned. We're trying to think of a machine which doesn't know what it goes like. So we as a human being know what it does. So it has got these 3 sensors, and it will try to learn to see, can I identify based on these sensors whether something is an apple or a banana? As simple as that. Okay. So now we know what prototype banana should look like. Banana should be elliptical, unless there is a round banana. I mean, to the best of my knowledge, one doesn't exist. Its texture should be smooth, and its weight should be less than 1 kilo, one hopes. Now for the apple prototype, we just want the shape to be round, and the other 2 have to be exactly the same as banana. This should be less than 1 kilo. So we know now as a learned user that the other 2 sensors were redundant. Okay? Good. So now we will design a single layer perceptron which tries to identify this thing. So remember, what did we say our perceptron does? It takes set of weights, multiplies with the input, and in this case we'll also add a bias to it to help it train quickly. Again, how does the bias work? We will see that. So essentially this is what we are doing. We have got weight 1, so we can write the weights as a row vector, and the inputs could be a column vector, so that the product becomes W11 times P1, W12 times Me2, and then we have got a hard limiting function as my activation function. Essentially, if it's less than 0, it becomes 0, more than 0, it becomes 1. Okay? And what we will say is my output of my decision making, my border of decision making will be 0, and this is why the activation function will come here in play here, right? So say if we have a banana, this will be my measurement, and my ideal learning function would have been this. My ideal learning function should only think of my shape. Okay, if my shape is -1, and if I want banana to be 1 as an output, my ideal learning function should have multiply -1 with the first one, the other 2 it should ignore. So 0, 0. Okay. Similarly, if my input was apple, then -1 times 1 would become -1, the output becomes -1, and I'm saying an output of 1 is banana, and output of -1 is an apple. Okay, so I've got a binary classifier, I have got a 2 input vectors, I've got everything just can take 2 states. Now let's hypothetically imagine that I get a rough banana as my input. It's possible. So so now my texture will have an output of -1 rather than 1. But my ideal perceptron will multiply that with 0. So I will still get 1, and my sensor will identify it as a banana. Agreed? Good. What will happen when I get an orange? I did not train my system for an orange. It has got a new input. It will give me an output, but it will be wrong output. This is one of the problems with machine learning based systems. They always fit. They always give you a function even though it may be a wrong function. Okay. So as I said in the morning that we are going to talk about different types of learning. So supervised learning is wherein we give an example of correct behavior. कि भैया ऐसे करना चाहिए था तुम्हें. Reinforced learning is we don't give any examples but grade a network based on its performance. Unsupervised learning is inputs are available, we have lots of data and all you have to do is to learn to characterize what kind of data it is. Right? So we are going to train this neural network now. So before I do the training, I will explain to you a 2-input neuron and then we will do the training for a 3-input neuron. And your task for today would be, if you have got your Python up and running or MATLAB up and running, to see if you can code it. Okay, it's no more than 3 lines of code, or 3 or 4 lines. So essentially this is what we would like to do is, if P is my input vector and T is the expected output. So I'm giving some input vector, gets multiplied with my weights, gets added with some bias, and T is my output. So say I have got sets of input and output. At P1, I get T1 as the expected output. With P2 input, T2 is my expected output, P, and so on and so forth. Okay? Now, we don't know what the weight of my system should be. So here, when we had done the training, we thought the best system should be -100. But initially, I don't know that because I'm learning. So we can start with a random weight, right? We start with, in this case, a random weight of 1 and 0.8. So we start with a random initial weight. We present the first input to this neural network. The input is 1, 2. The weights are 1 and 0.8. It multiplies these two. So 1 times 1 is 1. 0.8 times 2 is -1.6. I get a result of -0.6. I put a hard limit on it. It becomes 0. Now, originally I said for these inputs, my output should be 1. But my neural network is telling the output is 0, which means I have done a wrong job. So let's now try to come up with a rule to update my weights. So I did something incorrectly. My weights have to be updated. Okay. So let's think of the simplest rule in the world, which is whatever was my old weights, I just add my input vector to it. So for this input vector, you did a mistake. Just add to it to improve yourself. Okay, it's a very simple rule. So all we did was our initial input vector was 1 and -0.8, initial weight vector. And we just add the input vector to it, 1, 2, and we get new weights now. We still don't know if our design is perfect or not. Now let's present the second input vector to it, because it's going to learn from a large number of data inputs, right? So now we have an input vector of -1, 2. We do the same operation again. 2 times -1 plus 1.2 times 2. We get a result of 0.4. I get an output of 1, whereas my desired output was 0. So now I have over satisfied. I wanted 0, I have got higher. My output is higher. I could apply the same rule and say, okay, if I've gone higher, subtract my input from the weights. And we do the same thing again. So till we start getting correct results. So now we can come up with a theory. If my output is same as my expected output, don't do anything to my weights. They're fine. So if my error is 0, do nothing. If my error is 1, then add the input. If my error is -1, then subtract the input. And error is just my expected output minus my actual output. Okay? So as a result of maths, I could now write it as something like this. My new weight is my old weight plus error times my input vector, where the error could be 0, 1, or -1, and that basically determines whether I add or I subtract my input vector or do nothing to it. Any questions? No? Okay. Now we could go and now we can look back here and see what are things which we are doing. In the first step, we are multiplying numbers, then we are adding numbers, and then when we are updating our weights, we are doing the same thing again. We are multiplying two numbers and then adding numbers. So essentially, my entire operation is about multiplication and accumulation, multiplication and add. And this is why a large number of neural networks are actually designed on GPUs, because GPUs can do this multiply and accumulation work quite nicely. Good. So that's our theory behind it. Let's see if this theory can work on the apple-banana classifier. That was our original problem, right? Wanted to identify apple and banana. So this is what we know. This should be my... Let's go back and look at the sets because I have... So my prototype banana is when my shape is elliptical, and my prototype apple is when my shape is smooth. Okay? So this is my training vector now. If my input is -1, 1, -1, -1, my output should be 1. If my input is 1, 1, -1, my output should be 0. And let us do exactly the same thing which we did earlier, which is to start with a random weight. We don't know what the weight should be. And we start with a random weight 0.5 -1, 0.5, and also start with a random offset b to b 0.5, a random bias here. Okay. Now bias can be considered as something with zero input. There is no input, so bias still works. So neural network still gives an output even when there is zero input. So once again, we do the same thing. We have 0.5 -1, 0.5. Let's multiply these two, and can somebody tell me what will be the product of this row and this column? That much matrix multiplication has been taught to you guys. How much is this? 1 -1. So I just want the first part. Don't add 0.5 to it, just this part. -1, right? So 0.5 into -1 is -0.5, -1 into 1 is 1, and then so 0.5 into, so the first and the last cancel out one another and we just get 1. 1 plus 0, -1 plus 0.5 is -0.5. So again, I apply a hard limiter because that's the activation function I have decided for. I get an output of 0, which means what output I expected to get? 1. I've done a mistake. And I will follow the same criteria wherein whatever was my old weight, I just add this thing to that weight. Okay. So if I add the number as it is from 0.5, I will get these as my new weights, -0.5, 0, -1.5. And similarly, I update my bias as well. Let's apply the second set now. The second training set is this one, the one which has got an apple. Now, the only thing which has changed is the first input vector has gone from -1 to 1. Okay. If we apply the same set again, what will be the product now? There should be 1.5 here. Is that 1.5? Oh, sorry, 1. My apologies, 1. Right? So 1 plus 1.5, I get 2.5. This is a very large number. So if I do a hard limit of this, I will get 1. I'm still erroneous. Right? I've still done a mistake. So now what I will do? But I'm erroneous on the other side. So now I will subtract my weights. If I subtract my weights, I get a new set of numbers. Let's check if these new set of numbers work. Let's go back to our training data and multiply minus 1.5 with this set of inputs and see what so can somebody do this first multiplication? 1 plus 0.5, 1.5. There's a positive number, hard limit becomes 1. Yeah, the kind of sensor work. With this input, it gave me it gave me a result of 1, and 1 was banana for me, minus 1 was, or 0 was an apple for me. So, just in 2 training steps, despite using a very, very simple model, we have been able to train this system to get to a kind of we haven't got the ideal number system, because ideally we expected, my ideal training vector was expected to be minus 1, 0, 0. Right? I've not got minus 1, 0, 0, but I'm not too far from it either. I have got minus 1.5, minus 1, 0.5. So in due course time, it will forget. But despite its simplicity, it always converges to weights of a desired classification if the weights exist. It will take a long period of time, but it will always do that. Now that's the very, very simple individual block of a neural network. And we will use this as the fundamental of forming more complex neural systems. So hopefully you can see when I said the perceptron programming is not going to be very tricky for you. It's fairly simple, and I hope you to be able to do that. Before I let you go in peace today, because I did promise we will leave in about 1.5 hours, but so we are reaching that time. Now, historically, when it comes to financial data, we did time series analysis, because financial data exists in time series. People have recorded time-based data, right? And what we always did, we used some sort of statistics, okay? Essentially to say if the mean of something is here, the mean will remain the same, or the mean will move with the average or something. So we'll do a quick analysis of an hour tomorrow to see what are these things. But we always made very strong assumptions about market. And one of the assumptions was market is good and ideal. Market is never ideal. Okay. And the statistical methods which we used were things like either correlation, method of moments, goodness of fit, and various type of other statistical measures. Remember in the morning we went through slides to show how correlation can be a very bad example of looking at causality. Some two things that are correlated doesn't mean they are together, they are causal with one another. In a similar fashion, when people do Janam Kundli analysis, they look at Mangala and Mangali. That has got absolutely no correlation whatsoever. The problem with financial data is this. It's complex and it's highly nonlinear. It has got high threshold values. I will give you a very good example. So let's take an example which will put me in the least trouble. Should we take the example of buying a shoe or buying a t-shirt? T-shirt. So say you see a t-shirt worth 200 rupees and your budget is 150. You might try to convince yourself, okay, I had a hard limit of 150, but I really like this t-shirt, so I'll pay 50 rupees more. I don't know whether you can buy a t-shirt for 200 rupees in India or not, so please correct me if I'm wrong. But if it's a small difference from your heart, your brain will allow you to make that elevation. You will say, fine, I will eat less pani puri today to compensate for it. But if it's double the price, you will say no. But if I ask you where exactly is the threshold, because you started with a threshold of 150 and now you yourself are willing to move. So till where point you are going to move is very nonlinear. It's also very individualistic. Okay. The other problem with financial data is quite often it's a non-numeric and unstructured. So yes, I have stock indexes, and to some extent we have things like budget given by the finance minister. But many a times a speech by the finance minister can cause trouble. So if tomorrow the finance minister say that Bangalore has got too many techie people and I'm having water problem in Bangalore, I'm thinking of putting a 5% tax on people working in Bangalore. Just thinking. She doesn't put a tax. But that prices of Bangalore-based tech industries. 1 month later, she takes the statement back, it forgets it. Right? So a statement like this, now these are unstructured data. Sometimes they're text, sometimes they're images, recordings of some time. Right? So all of these influences financial business planning. This cannot be looked by a statistical based model. Okay? The other issue is many times it's high dimensional with sometimes many variables but very few observations. So there are many variables which are causing this thing, but we haven't recorded all of these variations for that matter. So one of the case studies, if we get time, we will be doing would be on liquidity analysis. And the problem which we had was how much money should I keep with me? You all have this money problem. Okay, so I'll explain this problem for an individual point of view. So once you start earning money, which I hope all of you will do soon, you have got this. So you need some money, keep some money for monthly expenditure. The rest you'd like to invest somewhere. If you don't invest, you're not getting any interest on it. So that money is going down the drain. So you could possibly buy a share or invest it into a fixed deposit. कहीं भी invest करेंगे आप, right? बैंक में. तो उससे आपको interest मिलेगा. पर अगर आप सारा का सारा पैसा invest कर दीजिएगा, तो आप उसी महीने bankrupt हो जाइएगा, right? या फिर आप गोलगप्पे नहीं खा पाइएगा. So here is this dilemma you have. कितना पैसा रखें? So how do you do this? You have do some calculation based on your past analysis, right? पेन पेपर का इतना लगा था, इतना ही लगा था, तो इतने पैसे जरूरत काम चल जाएगा. And then 1 month somebody hits you and you have to go to a hospital. या फिर आप बीमार पड़ गए, आपको दवाई खरीदनी पड़ी. So all of a sudden, all of your analysis goes down the drain. So it's a highly dimensional data analysis. A simple liquidity analysis of an individual. मैं अभी country का भी नहीं कर रहा हूँ या किसी company का नहीं कर रहा हूँ, एक individual की बात कर रहा था. Right? And quite a lot of it had few observations. For example, अगर आप अपना कर रहे हो कि let's try to find what is the probability of me needing to see a doctor. You could do that calculation, right? कि हम इतने साल के रहे, आज तक इतनी बार गए, हमारे compatriot जो बाकी लोग हैं वो इतने साल के हैं, वो आज तक इतनी बार डॉक्टर के पास गए. So you can try to come up with a statistical measure of what is the potential cost of healthcare for you. That's what the insurance company do it, right? They try to compute what is the typical insurance cost I should charge this person so that I'm not in loss. Okay? But there are very few observations on it. And there lies the issue. For example, we don't have enough data on every different lifestyles of people in Odisha to come up with one measure of health insurance for men or women in Odisha. Okay? And this is why we think that the financial machine learning provides a better opportunity to understand this data than pure statistics-based methods. To further criticize statistics-based method, we will of course learn to them. And please don't say this to your economics professors because they believe statistics methods are ideal. Right? What we think is that the system, the world or the firm or whichever you're working should be thought of as a black box. We don't know the relationship. There could be many variables. Let the system learn on its own. The other issue is that finance is not a plug or play kind of system. People believe that business world is even more complex than driving cars or identifying cats in YouTube videos. And you might say self-driven cars are already fairly complex. Particularly, India में तो कभी self-driven car चलेंगे ही नहीं. You never know, चल भी जाएंगे. And there might be a model wherein you have to say is if you find a space, fit yourself in. That's the model of driving, right? अब मेरी पिटाई करोगे नहीं सर हम लोग तो एकदम सही सही गाड़ियाँ चलती है हमारे देश में एकदम लाइन से चलती है. Right? So the machine learning models, you give them a data, they will find a pattern in it, even if the pattern does not exist. And that could be problematic for decision makers. The reason why it's also problematic is, as a decision maker, understanding what the machine learning is doing or understanding what the neural network model is doing is very challenging. But now you're going to decide about billions of euros of investment or the healthcare of your country based on a model which you do not understand. It's a black box model, right? खुद अपने आप को सीख रहा है क्या करना है और आप डिसीजन ले रहे हो जिसको आप समझ नहीं रहे. जैसे अभी आपने अपनी लिक्विडिटी डिसीजन ली बेस्ड ऑन योर ओन गट फीलिंग कि इतने रुपए का बाहर खाना खाऊंगा, और अब आप कर रहे हो कि भैया लेट्स जस्ट गिव ऑल द डेटा टू दिस मॉडल और ये बताए कि ओके हमारे ज़माने में 500 रुपये वॉज द मंथली एवरेज खर्च. आई डोंट नो व्हाट्स द टिपिकल मंथली कॉस्ट ऑफ एक्सपेंडिचर एज ए स्टूडेंट दीज डेज. Don't worry, your secret is safe with me. How much? 2,000. Is that the number? 5,000? Okay. Of course it depends. It's individual. इसीलिए तो डेटा कलेक्ट कर रहे हैं. सबका एक ही नंबर होता तो फिर काम ही आसान हो जाता है. Right? किसका? Boys का? क्यों? जेंडर रिलेशनशिप्स चेंज हो गए क्या हमारे जमाने से? लड़कियां खिला रही हैं क्या लड़कों को आजकल? Are you married, Babu? That's why you are making that statement. Again, now that's a financial data which you have assumed without having a data set. And I'm not pulling your leg on it. I'm telling you this is the problem of a finance manager he has. So he has to decide finances of a female employee or female clientele without knowing. There's no data. पर उन्होंने assume जरूर कर लिया कि लड़कियां होंगी खर्चा करती ही होंगी, हर बार बाहर खाने जाती हैं तो मेरा बजट बड़ा बनाती हैं. How do you know when they go on to eat on themselves, they don't spend that much money? Right? So we have a problem of finding a pattern. We have a problem of not having enough data. We have a problem of overfitting. And overfitting can be very problematic. This is more problematic than statistical based models, which we will talk tomorrow. The worst problem which we have in machine learning when it comes to financial information is जब हम scientific data की बात, देखो हमने machine learning शुरू हुई है तो computer vision से, right? Cat in YouTube videos या फिर identify a face or cluster people between men and women, identify the face of a person. This is where it starts from. Fortunately, here the samples are independent and statistically not dependent on one another. मैंने उनकी तस्वीर ली और मैंने आपकी तस्वीर ली. These are statistically two independent figures. Or एक और example I'll quote from a book or from a presentation from Marco Lopez de Prado. I'm citing his book here. So if you're looking at biological samples, say आपने टेस्ट किया कि blood test ले रहे हैं आप सभी लोगों का, 30 लोग हैं सबका हम blood test ले रहे हैं. I know each tube will only contain blood from one person, right? Financial machine learning is about, okay, this tube might have 0.9 blood from one person, but 0.1 from everyone else, right? To give you an example, आपने 2,000 रुपए कहा कि मेरा monthly expenditure है, right? But this, you don't know कि कल को institution tuition fee बढ़ा देगा, ज़्यादा पैसे देने पड़ेंगे, right? That we haven't, so there are factors. Or for that matter, if everyone else has decided to go for a picnic somewhere, everyone else has influenced yours, so your decision making is no more independent. So every data point is related to other data points one way or the other. So we don't have independent samples to work on. And this is why direct translation of machine learning models, which we have learned in every other field of science, to business is tricky at best. So what we will do tomorrow onwards is we will be looking at lower hanging fruits, not to predict कि कितने पैसे चाहिए. Actually, that might not be a bad idea. आप लोग एक data create करोगे. Let's try doing this thing. That's for fun. Okay? You all have your bank accounts, right? और आजकल तो आप लोग सब बैंक से ही खर्चे करते हो, right? So you can have a financial statement last 12 महीने के अपने और 24 महीने के. So we will do a randomized test. Okay? So we'll omit your names completely. Just look at what is your total expenditure per month. Okay? It will be surprise. And then we will do a 2D table of everyone and your monthly expenditure over 12 months. Now we'll have a grid of data, right? On x-axis, we'll have, say, 15 students and 12, so we'll have 180 data samples. Let's try to learn from this and see if it tells us. And then we will try to classify and answer the ultimate question of our colleague here. Do girls spend more than boys? मेरी पिटाई होने वाली है किसी दिन. घर में पहले पिटाई होगी और फिर मेरी फीमेल कॉलीग्स पीटेंगे मुझे. ये कौन सा रिसर्च प्रोजेक्ट है? Right? So let's try to answer that question with data. So हम एक काम करेंगे. I will create an online repository where without giving you personal information, you can upload these numbers. Okay. We will then try to divide it based on gender and maybe age, and then we will see how it goes. Okay. And then we will know अगर लड़कियां सच में ज़्यादा खर्च करती हैं. Well, considering कि data set बहुत ही छोटा है, most probably हमारा आंसर भी गलत होगा. But that also tells us another problem of financial planning. Data sets छोटे हैं, haphazardical हैं. We don't have continuous data of everything. So despite the fact that finance people have collected a huge amount of data, they don't have all the data. Well, no one can, because they don't know what are all the variables which have gone in play here. Okay. For example, people living in Rourkela may have higher costs than people living in a rural village nearby. Right? And I don't know, is Bhubaneswar costlier to Rourkela, or is it same price? Is it only the housing which is costly, or is the... Okay. So that becomes a very interesting problem here. Who is more expensive? A Bhubaneswar-based girl or a Rourkela-based boy, or vice versa? Yes, but now we are looking at a metric of a person. So if a father wants to, a parent or want to send their child to study in this region, they would like to know an average kind of figure, right? So let's at least do mean and standard deviation. So if are all of you living away from your parents, or are there people living with their parents here? So you all are living away, right? तो आपका financial data completely independent to your parent होगा. In the sense कि ये नहीं कि आज का खाना मम्मी पे कर रही हैं, खुद ही पे करना है, right? अपने अकाउंट से ही. And I'm kinda hoping नहीं आप लोग इंडियन हो, 3-4 बैंक अकाउंट तो सब लोग मेंटेन करते हैं. This is where life would have been easier if everyone had one data extraction. Would be easy, okay? But let's anyway do this experiment. Let's try to do of 2 years data, because that will then also tell us the seasonal fluctuation. आपके expenditure में भी seasonality रही होगी. So tell me, why will there be a seasonality in your expenditure? So आप हॉस्टल में रहते हो? हॉस्टल में तो हर 12 महीने किसी न किसी का बर्थडे रहता है, तो वो एक्सपेंडिचर, अच्छा अपने बर्थडे में जाना, हाँ फेयर इनफ. हाँ मजबूर. But it's a cyclic, हर साल आएगा. Right? And actually what you would see, for those who have lived longer, you will have a cyclic fluctuation like this. Every year it keeps on increasing because your number of friends increases. And then 1 year drastically decreases. जिस साल शादी हो जाती है, बीवी बोलती है अब किसी को नहीं खिलाना है. And the vice versa. आपका husband भी कहता है और किसी को नहीं खिलाना है. Okay. So let's do this calculation and let's try to figure out what are the sources of cyclic variation. So my original plan was to give you temperature data today. So I'm going to post temperature data from Oxford from 1853 onwards. So we have 170 years of temperature data. I tried getting the data for Rourkela, and I could only get for last 25 years. So that could be another experiment we could do. is let's look at the rainfall data and temperature data and try to predict what is going to happen next year, assuming nothing drastic is going to change. Again, हमने already assumption मार दिया, right? कि nothing drastic is going to change. But temperature data is the most seasonally nice data we can carry, and same with the rainfall data, right? Seasonality होती है, variation होता है, so you can look at that thing very easily. But I think this is a better experiment. Let's look at your spending figures. Good, let's stop for today then. Right? Thank you very much.